here for the introduction. I'm Hazel and I work at Hello Games. We're a little indie studio based in the UK, and we're working on No Man's Sky, which is an exploration sci-fi type game, but all based in this procedurally generated universe. So things I'm kind of going to cover in this, I'm going to give a bit of a background to the project and what we're doing and our aims for that. I'm going to talk a bit about structuring a game and a project that involves a large amount of procedural content and kind of ways to go about that. I'm then going to break it down, work from the top down for generating a solar system. So looking at how we create a planet, how we populate that. And then I'm going to round up with some of the general experiences we've had from the project, things we've learned and things we'd do differently next time. So to give a bit of a background about the team, we're still a really small team. We started out with 4 people working on the game, and now we're up to 13 of us, and 7 of those are programmers, so we're quite code heavy. Apart from that, we have a producer and a designer, and the rest are all artists. So again, it's quite a dev-focused team and a lot of coders. We're working on our own engine. At the start of the project, we did evaluate other things, and it's not necessary that you create your own engine to work on procedural content, which is something that I've heard a few times. But for us, in terms of profiling and performance, just really knowing our own code base is something we can afford to do with a team our size, so it's a route we went down. That's all in C++. Again, we experimented with some scripting and things, but because we're a code-heavy team, that didn't really make sense for us. Is working on console and PC to give you an idea of the kind of hardware limitations that we're facing. And one of the most important things is that all the generation we're doing in-game. We're not kind of baking anything offline and then loading it up. We're having to do it at runtime as the game is going. So our philosophy, because I guess I was feeling really pretentious when I labeled this slide, we're definitely making a game. We're not making a tech demo. We're not trying to make some passive universe that you can kind of experience. Everything we do is focused on you enjoying this game, you spending time in it, and that includes the content that we're generating has to be something that makes sense in a gameplay context, and also the way it looks, and also just where we spend our time as programmers. The other part of that is that we're making a fantastical sci-fi type game over simulating our universe. I'm sure if we wanted to just recreate our solar system, we'd go down a really different path in terms of the kind of generation we'd be doing. But actually, we want something that's quite artistic and different. It's really important to us that the artists on the team, even though procedural generation can seem like a topic that is really code-heavy and that our programmers have to direct, it's important that they can do their jobs, that they can create concept art that we can work from, that they can direct the assets that are happening in-game. And finally, it's really important to us that procedural generation is completely unimportant to the end user, which can seem like a stupid thing to say when we're a game where, when people talk about it, probably the first thing they mention is that it's procedurally generated. But to us, this is a means of making content. If you had like an infinite number of monkeys with an infinite number of Maya licenses, then it should be the same result as having algorithms create it, and it should be the same result as having highly trained artists with infinite time work on this. That would be the ultimate goal of procedural content for us. So in terms of why we are using procedural content, there's the really obvious things like the scale of our world. Even with a really massive team, no one can populate that with hand-edited content. But as a small team, then we definitely don't stand a chance. But there's also other reasons why we choose to take this approach. We want the outputs to be unexpected, not just for gamers playing the game, but for us as a team. We don't want everything to be mapped out and certain. We want it to be interesting and different as you're playing through. And we want people, like this sounds like a buzzword, but we genuinely want people to have individual different experiences. This shouldn't be a game that you play through like a film. It should be a game where you have your own stories, and you can tell your friends about those stories, and they've had something different happen. And for us, routes to produce that can quite often involve player interaction or alternatively user-generated content. But we want to create a game world that inherently allows those situations to come about, and that's why prop gen and not knowing all the rules and not knowing how everything's going to play out is really important. So to give a little bit of information about how we've structured the project in a technical sense, we have an engine that's really agnostic to all the procedural generation stuff we're doing. So, I mean, we still have to implement generation techniques, but that's really separate to how we render things, how they live in our resource manager, and that's really helped our workflow through the project. That means you can start with a static model and then replace it with procedural content, and if it's not interesting enough, you can replace it with new procedural techniques until you get something that's exactly where we're trying to go to. And also, we work on a real mix of really specific procedural generation techniques, but there are also some really general things that we're able to apply throughout the game. And again, being a small team, being able to write an amount of code that makes sense rather than write something really specific that's planned from the get-go for every single asset we want to create is really important. So being able to pick out those things and work in a smart way is super important. So I'm going to talk a bit about how things are generated in terms of how they're actually generated, starting at a galaxy level. So starting with this video here, this gives you a bit of an idea of the scale of content that we're generating. So this is a galaxy. All the points there are individual stars, and those are solar systems. So they have their own planets and things like that. But the other reason I'm starting here is that's where we start our generation process. So all of those points, their position in space, gives us our initial seed value that we're going to feed into the system. So we have a little 64-bit seed that is our starting point of every little solar system. So we use a kind of multi-layered generation approach. So like I said, we start with that seed, and then we're going to feed it through a series of different generators. So at each point, we'll start with the minimum amount of data that we need to generate a particular asset. We'll be able to feed that in, and then we'll have our complete data output for that object. The reason we need to keep our data really minimal isn't just for hassle reasons in terms of coding, but it's also because a lot of this will end up stored on servers and that kind of thing. So being able to reproduce any asset from a very small amount of data is what allows us to make efficient use of that space. And those generators tend to be collections of functions. Some of them will be things that are shared between different generators. Some of them will be really specific, like I was saying, but I'm talking about actual classes filled with functions when I talk about those. It's not some sort of abstract concept. So in terms of our generation data, all of the data that we generate, so that might be the information that lets you render a planet, or it might be a mesh, or it might be the information that lets you create a mesh. All of that is an asset. It all lives in our resource manager. We're able to serialize all of it. And that sounds like a kind of obvious step, but it's so critical in being able to make this game work, because at any point in our chain of generators, we can end up with kind of unexpected things when you're applying rules after rules on top of each other. But this means at any point we can step in, we can look at what's going on, we can debug the generation process, and we can also manually edit the end results and see how things would work out. So maybe we don't have a system for generating something yet. We can step in and edit the data and have a play around and see what kind of things we're going to need to write the code for. So coming down from our galaxy level generation, we get into an individual solar system. So the kind of things we'll be generating this stage are not just planets, but also the atmospherics for the galaxy, asteroid belts, ships and fleets and their behaviors, whether there's a space station, what kind of factions are active in the area. But the bit I want to focus on for this is really generating an individual planet. So when we talk about input for that, again, it's a minimal thing. So it is a seed, but a seed doesn't really give you enough context. Imagine if we generated, I think it's quintillions of planets across the galaxy, and everyone had a different seed, then everyone would just be a random planet. It wouldn't have any context. So we supplement that with additional information. For example, the planet's size and position in space, its distance from the sun, so we can calculate how its climate should behave and its atmosphere and things. So I'm going to go through next and talk a bit about how our planets are structured, because that's really what will make sense of the generation techniques we're using to create them. So planet structure. Our planets are spheres. They're not just spheres when you look at them in space. They're spheres when you stand on them on the ground. So our physics is done on a sphere. our bounding boxes, our axis-aligned bounding boxes are slightly different on one side of the planet from another, depending where they're rotated. There are a lot of things that come from making your planet spheres that are tricky to work with. But in terms of having continuous generation around a planet, there's no real alternatives in terms of mapping planes to them that'll work quite as well. But that said, spheres are a super bad shape for us to store our data in. So our data for the planet, our voxel data, is stored on the faces of a cube. So we kind of have to go through a projection process. So we generate our planet as if it's a sphere so that we don't have kind of weird artifacts at the corners. We project that to our data that's stored in a cube, which means we do get slight differences in voxel densities from the center of the planet, maybe to the corners of the cube, but that's not that big a deal. And then when we come to generate the vertex data, we have to reproject that all back out to be on the surface of a sphere again. Like I said, our world is made of voxels, surprising probably no one. We split those into regions of about 32 meters cubed, and we process each region individually. We have to have a bit of an overlap so that we can voxelize them correctly and make sure we don't have gaps in our terrains and things. But most importantly, we retain that data throughout the whole game. So if someone comes and blows a massive hole in a region, then we've still got that and can immediately re-edit the data, repolygonize it, without having to go through the generation process again. So we can have terrain editing just really quick like that. I wasn't going to bother with this slide, but then someone said to me, oh, who cares about memory in modern games? And I care quite a lot about memory. I'm sure a lot of people do. So our individual regions are 32 by 32 by 32 voxels, and each of our voxels is down to about 6 bytes of data. So in terms of a single region, we're talking maybe about 200 kilobytes. And then when we get to like a kilometer cubed, we're talking gigabytes of data. There's no way we can support that, obviously, but it's not just in terms of the amount of data we're storing. The amount of voxels we process immediately relates to our performance in terms of generation, how long it takes us to generate a region. So anything that's reaching our hardware limits is definitely reaching our generation and our performance limits. So instead, of course, we use LODs. We use them as regions around the camera that are overlapping. We keep all of our lower LODs around when we bring in newer ones over the top of them, again, just for speed reasons. And another thing is that our lower LODs each LOD is incrementally twice the size of its predecessor, but we also scale them in a non-uniform way, so we reduce the voxel density inside them. And that just lets us get slightly nicer terrain in the second LOD down, because we can keep a higher scale in the Y from the XZ, and it makes everything just look a little bit nicer. The terrain is a little bit more recognizable. So we have our LOD regions, and we stick them in an Octree. Hooray. The image on the right there, the red line around it, we kind of think of as the radius of the planet. So this image isn't a top-down view, it's more of a cross-section of our cube. So our planet exists in this Octree cube, with our regions existing around the outside of that. So that means we can quickly access things that are on a particular face of our cube that we're then projecting to a sphere. But it also means if we want to let people dig further down, we can start increasing the region density there, and we can build up from things to get higher mountains as needed without creating loads of new regions. I want to stress that we don't store our voxels in an Octree, we store our voxel regions in an Octree. We're not using sparse voxel Octrees. We find things faster just using a flat array of voxels. So here is a video of us going down to a planet, and things to look out for are like the lowest LODs of terrain as you come down, and then seeing them generate up close, and then it flies around. So moving on to this one, these are really old videos. I should probably say that because there's a lot of artifacts in them that were fixed since then and are super gross for me to look at. But the reason I'm showing you an old video is that this is where you can really see those LODs popping in. So we kind of dither one LOD over the next, and you can get a real sense of how we're doing that. Throughout the project, we kind of go from really optimizing our generator and our polygonizer so we can do that really quickly, so that we're not seeing those LODs popping in, to adding loads more stuff to our generator, so then you can see them again, to fixing it. But we're pretty confident that what we have now looks a lot nicer, and what we will have will look super nice, hopefully. Yeah. Okay, so now you know where those regions live, what they're composed of. There's a process that we go through for each of those individual regions in order to get it to be something that makes up our game world and get it renderable. So we go through generation. I'll talk a bit about that first in a moment. Some other steps, polygonization. We use a bunch of different polygonizers. So we use dual contouring for the majority of the terrain, but we also have some things that are very cube-shaped, and we use Procedural, and we have some things that are very flat plane-shaped, like water. So we have a faster polygonizer for that, and we just run them on different sets of voxels each time until we have all our vertex data. As I said, we then take the vertices, we stick them back out on a sphere because they've been living in flat plane cube world up until this point. And then once they've got their final position in the world, we have to start creating gameplay data. So we have to construct our physics meshes, and we have to put together our AI knowledge and some other things. A thing about generating terrain on the fly obviously means that we can't do any sort of pre-processing that you might normally do on terrain. So we can't be baking in any lighting, any occlusion or anything like that. If we want it to exist, we have to do it as the game is running. So we tend to do these tasks off on a thread, which doesn't really remove the problem, but it at least lets us run at 60 while doing all this stuff all of the time. And then our final step in the process is decoration. So that's just where we take our terrain and all of our information that we've generated about it, and we cover it in plants and trees and life and rocks and all the things that make it look like an actual planet rather than just some poly mesh sort of thing. So, generating our actual terrain. We've got some requirements for what our generators need to do in order to work in the environment that I just described. So we need something that's directable and consistent, so we need to be able to edit input data, and obviously we'll have another generator that will be creating that input data, but it needs to be data that makes sense and gives you the output that you want. So if you edit some data to say, I want big mountains on this planet with some really deep valleys, we need to be able to have a human look at that data and know what that means and be able to create it before we can have a generator look at that data and be able to create it. We need to have it all run in real time, obviously. We need it to be really varied, so no kind of Perlin noise terrain. It needs to genuinely look like there are places, and they're distinct places, and they're different, and you can make out features in them, and that they'll work with gameplay, so you can navigate the terrain. It can look like there are meaningful routes for the player to follow, because if you just generate a mountain range and stick a person in it, they're not going to have that great a time. Even though we want people to feel lost and like they're exploring, you still need to be considering paths they're likely to take as you're generating. We want to create real-world and abstract shapes, so we're not just looking to replicate things that are on Earth, although we have tried to look for the weirdest places on Earth and then tried to make a generator that will work for that. We also want to create things that are completely impossible on this planet, but we've seen on the cover of old sci-fi books and that kind of thing. It needs to be really easy to modify and add to. We can't afford to have a system where every time we want to create a new feature in the terrain, we have to rewrite all of that code. It needs to be something that's modular and that we can keep adding to over time. And finally, the biggest one, it needs to be data local. So what I mean by that is every time we generate a voxel, we don't know whether any of the voxels round about it have already generated. We only know about it in isolation. So the only input we can have to that generator is some general information about what we want for this area of the planet and this voxel's position, and that's it. We can't do things that involve refining that over time. We can't have methods that involve real erosion. So the methods we use have to look like we're doing those kind of simulation steps, but they have to get right to the end result. We need to be able to say, I want a terrain that looks like it had mountains and was eroded for 4 million years, and we have to be able to generate something that looks like that, but we can't go through steps of incrementally eroding that terrain because it would involve the kind of blurs that would need to know information around each voxel. So to start off with some local techniques, this is the most basic, but it kind of gives you an idea of the kind of noise cloud-based technique we're talking about. Perlin and simplex noise get a really bad rap because of the picture on the bottom right. It's blobby, there's no distinct features, you're not really getting anything of interest from that, and we've probably all seen too many terrains that look a little bit like that. That's probably the first thing I ever generated right there. It's still pretty bad. So these sort of things are really insufficient for generating terrain, but they do work as a basis for all other things. And they also explain kind of what I mean by a local technique. And then moving on. So it's not like those noise types are without meaning. You can get a lot more from them just by considering mathematical operations. So this is just to show that you can start with a noise generation technique that's really quick, really simple, and just by doing a little more work on it, you can have something that's starting to look like something we might use in game. So the screenshot on the bottom right there, that's got some Perlin noise with a threshold value on it to get those weird floating tubes. That's probably the most directly we'd ever use a technique like this. Generally, what I'm talking about is building up a toolkit of all these techniques and using them together to break up any of the distinct shapes. But if you wanted to start looking at a cave network, you can already see how you're starting to get shapes that would lend themselves to that if you did a bunch more work on them. A lot of people think of noise-based techniques and only think about things with blobby edges, so I just wanted to take a moment to talk about things that have sharp and distinct lines to show that you can get that kind of thing if you want to be creating terrain that looks more industrial or less natural. If you want straight paths and cliffs and things, then something like picking points and calculating the distances, something as simple as that can start to build up those shapes. And then anything that you want to add to the terrain, you can be thinking about any mathematical solid that you can create in a 3D voxel field. So a good example of that is the super formula. That's something that Sean's been looking into recently, and it's a simple formula laid out in the paper there that just lets you create some really interesting natural shapes. And again, that's not really the... You can dot them around the terrain, like the screenshot there, and that's just to give an example of how it would work. But it's the kind of thing that we'd layer with other techniques, maybe use some turbulence or add or subtract them to other things in order to create something that's actually interesting. Nothing by itself is really interesting enough. The key is having this toolkit of loads of different techniques that you can use in different areas until you get something that looks like the goal you're seeking. So then, given that we have a few techniques in our toolkit, and we have a big list of techniques in our toolkit, how do we actually generate that terrain? So we start off thinking in 2D. So obviously we're working on a sphere, so nothing is really 2D. So really, we're thinking about a sphere in a big 3D field of noise. We're dealing with 3D positions, but we're thinking about just the surface of that sphere rather than shapes like mountains and things growing out from it. We use some basic techniques to block that out, and we're not really saying that any particular area is a mountain or any particular area is a field. We're saying more like the extent to which any given voxel could be a mountain, the extent to which it could be a river, that kind of thing. And because we're doing this in 2D over the surface of the whole planet, we can use our more expensive techniques here, and it's not a problem before we move into 3D, which we're doing for every voxel. So thinking in terms of our sphere again, you can imagine this as layers moving out from the sphere, like mountains on a planet, that kind of thing. And this is where we can take our 2D noise, we can consider it to be a density, and we get your really basic height field. And it's pretty obvious to see that height fields are insufficient for interesting terrains because there's no case where you can get overhangs, you can't get tunnels, you can't get caves or anything like that. So it's really critical to move into 3D, and I think for really basic terrain generation, that can be often what it's lacking. But there's a lot you can do there, from just turbulence on shapes you've already generated on your height field to constructing whole new solids like things from the super formula or methods of digging tunnels into the world. You can be adding subtracting as well as adding through this and any other operator you want. So, okay, here's a quick video with some of our terrain stuff. I think it's kind of heavy on tunnels, but you can look through and see some of the ways that we're breaking up areas of the world. So yeah, this is where we start to get something more fantastical. So you probably don't see floating islands on Earth, but we're big fans. Going to things with rocky valleys, and sorry, this is all moving quite fast, to more natural terrains. So moving on. So now that we have our terrain geometry, we really only have a mesh. We don't have any texturing. And in order to think about that, we need to think of our voxel materials. So I said that our voxels are about 6 bytes before. The values that those are actually composed of are a density and a sharpness value in order to create our terrain mesh, but additionally, 2 different materials and a blend value so that we can tell the extent to which a voxel is in a particular area and have nice transitions between patches of grass and rocks and different types of rocks within other rocks. This all gets carried through when we polygonize so that we have this information in our vertex data, and then it gets passed right through to the shader, so at any given point we can be relying on the materials for our terrain. So like the audio system will use it, for example. It just underpins what our world is made of. And then actually texturing the terrain. So we don't do any of the texture generation in the fragment shader. We create texture atlases ahead of time to have the textures that we want to use on the terrain. So we build up an atlas of all the types of materials that we have in an area and the texture that we want to use for them. We use slope textures as well as textures for different materials. So you can see in the screenshot there, we've got something that's all made out of rock, but we're going to blend based on the different gradients and the different type of, the different way that's likely to look, so that we can go between different textures there. And then in terms of texturing the planet as a whole, we use a triplanar approach. So we're applying triplanar texturing to the planet as an entire sphere. So we'll be projecting the same texture along different axes onto this sphere and blending between them at areas that aren't distinctly on any one face. And a really interesting artifact from that is that if you blend on a little sphere, you have a little blend zone. And when you blend on planet, those kind of fuzzy areas that are circled will be kilometers across. So you can have a whole area that doesn't have any distinct sort of texturing. So we need to think of more interesting ways that you can blend between textures in that point, and that can be both tightening up that zone, using textures to allow us to blend between others, using masks and things, but just to keep our texturing distinct right around the planet. So for a quick look at texturing, on a kind of green planet, you can see how we're going between rocks and the different kind of grass surfaces there. It's not super distinct, but also while we're looking at the terrain on this one, you can also kind of imagine how the terrain's looking one way while we're flying over it, but it probably looks quite a different way when you're up close as a person, and we have to work different scales of textures into that to make sure that everything looks okay while you're up high, but looks equally detailed when you see it really close, and everything plays well whether you're flying over it or whether you're walking along it. So moving on from generation to actually decorating our planet. When we first come to create our planet, that will normally be at the time that you arrive in a solar system. We have to make up a set of all the creatures and the way that they interact, all of the foliage, the rocks and the plants and the trees. We have to create the models for those, but also the data that makes them meaningful. So for the trees, for example, we'll create a whole load of plants and things like that, and then we'll categorize them into things like grass that might cover the world, some really big and distinct sort of hero props that you will only want to see occasionally, and you'll want to be kind of different every time you see them. And then we're able to create placement patterns on the world. Those placement patterns we can create in a pretty similar way to generating terrain. We just need all those different noise-based techniques in order to create patterns that look interesting, but also look aged, like we want a forest with loads of undergrowth to look like something that's really mature or something that's newer with smaller trees, and we need to be able to think about that at pattern generation time. In terms of creating those individual objects, the artists are responsible for creating base rigs and shapes for those, but then we put together parts of geometry, like for this tree, and once those are assembled, we texture them, and we texture them again by combining loads of layers of textures, recoloring them individually, and creating masks that match that. Finally, to make the shapes interesting and distinct, we apply deformation. So we do that based on simple animations that we can blend between. So for example, for a creature, that might be elongating its neck. For a tree, that might be curling it up or bending it over a certain way to look like it stood in the wind like that for a really long time. Just as you can see from stepping between the second last and the last image there. So then when it comes to use those in-game, again, because these are all created online, then all of the gameplay data needs to be created by us online. We use a component-based engine, so then building up our objects in the world, whether those are static trees or ones that have some sort of gameplay interaction or ones that do something when you shoot them, anything like that we can build up with components once we're in the game. But everything else has to be done live as well, so rendering out imposters, creating thumbnails for use in our engine, creating lighting, and also putting together things like behavior trees. So for all our spaceships and all our creatures and things, their interaction and their behavior has to be built up in-game, depending on the type of characteristics that we've specified that they have. So here's some of our decorated worlds. Things to look out for are, for example, ways that we cluster trees. So we do that both from a realism perspective in terms of building forests, but also in terms of what our art director really likes to talk about is if you have an individual tree, that's not very interesting. If you have 3 or 5 trees, that's quite a nice scene. But if you have 3 or 5 trees in a cluster with some medium-sized plants around them and then some little plants at the bottom, that's where you start to get something that people actually want to look at, that you can look at any scene and think, oh, I could take a screenshot of that, and that would be nice. So finally, I just want to go over a few things that have kind of been working for us and some things that we're thinking about as we keep going, things we might change if we worked on this kind of project again. So a thing that's really worked for us is the art direction in terms of the response that we get from artists, in terms of the way that they're able to lay out the game, but also in terms of everyone on the team thinking about both design and art when they're creating something. There's no one who can step back from procedural generation and say, oh, just do my job under the hood and kind of make this work. Everyone needs to be focused on the final result all of the time, on what's actually being output. We work from concept art quite a lot, but we can't work from it in a traditional sense of having a really nice painting of a scene and then exactly recreating that scene. And that's been quite a shock, I think, to move from that way of working to having a really nice picture of a scene and then loads of different scenes that are kind of a bit like that, hopefully in the right ways. So we rely quite a lot on paintovers as well. So we'll go from screenshots and then we'll have an artist who'll do some work on them in order to get an idea of what should be changed. All of our assets can be procedural, and any asset can be procedural. So anything that we think is not working, if we have a texture that looks really plain, we can write a new generator that will suddenly make that much more interesting, and we can just plug that in with the game and the way that everything lives in the engine. And we treat all of our assets in exactly the same way, regardless of whether they're generated or not. And in terms of our workflow, that's been a really big boost. And then finally, a massive thing for us has just been thinking about what content is interesting and where do we apply our time in terms of generation. So what makes an object unique? What changes are obvious, whereas what changes could be completely meaningless. Like I could spend loads of time writing a generator for really detailed textures on objects and you'd never see any of them. Or I could write a generator that'll place things in a completely different way, and that could have a really stark difference. So you need to be able to think about that ahead of time, and it's okay to think about that as the game goes along. And what kind of repetition is okay? So if I made every individual blade of grass really stand out, then you're not going to care about anything in the world. And similarly with the frequency of content, if I make every single thing really cool and unique, then nothing is cool and unique. We start from a kind of frequency of having 90% boring stuff and then 10% cool stuff. So when you see something cool, it's like, whoa, that really stands out to me, rather than like, oh, it's another one of those planets with all the bird things that are cool, I guess, and some trees that are colored. It needs to be an important moment for the player. So yeah, to summarize, structure the game for flexibility. We build up a toolkit of techniques, and I think that's a really good approach for generation. Start with things that are general, but then tailor them as you need and as you go on, and as you can see where you can genuinely make an impact. And finally, nothing in procedural generation is a solved problem. You can't just plug in a solution and have it work. And anything you do is kind of OK, as long as the results are good. So yeah, that kind of wraps up what I have to say about No Man's Sky.
First of all, it all looks amazing.
Thanks.
And I was wondering, what is the extent to which you can deform the terrain and whether it persists at all? And if I started poking holes in random planets, how would you deal with the sheer amount of destruction the players can cause?
So that's kind of both a technical question and a design question. So technically, we can deform any of the terrain as much as you want. We have all that. All the data that you can see at any given time and see to destroy, then we can also edit and deform that and repolygonize it almost right away. So you can edit that quickly. In terms of retaining data, we definitely have systems for retaining changes that you've made. In terms of those changes applying to other people, our design philosophy is that if other people are going to see the change you make, it has to be a really impactful thing, and it has to be a really big change. So if you dig a little hole in the world, that probably wouldn't be something that would carry over, but much bigger changes than possibly.
All right, we got a question from the stream. Do you run any of the heavy BCG calculations on the GPU? If so, what are they?
No, at the moment we do all of the PCG calculations on CPU because we need our GPU for rendering. But that is a good point, and I think if we had to move something onto GPU, we'd possibly move Polygonization, because that's quite general code, rather than something that we edit a lot, like generation code. So the generator has to be something that everyone on the team can kind of look at and work with and make sense of. So moving that onto GPU would probably make less sense than something that we can rewrite and probably not touch again.
Have you guys considered making your planets box-shaped and not sphere-shaped?
We've had people say that. I mean, technically, I guess we could. We'll consider that, and toruses, and we'll see.
Another question from the stream. Can you tell about the allocation of CPU time and memory for generators and other systems?
Can I talk about the allocation of memory and
CPU time?
And CPU time for generation. So in terms of milliseconds, not off the top of my head, despite the fact that we've been staring at it for a while. But generally, we'll have generation and polygonization threads running all of the time. And they'll probably, we can generate the whole planet in probably a matter of seconds rather than milliseconds, but it'll be sub 5 seconds sort of thing. And that's a whole planet, so it's a fairly small amount of time, but it is a significant enough one that it has an impact on what we can do otherwise.
Hi, thanks for the talk.
Hi.
The biggest difference that I saw between, let's say, the static screenshots that you show from the game and the actual demo videos is not about the LOD popping or the artifacts that you were concerned about, but the biggest difference from my point of view was the distance, the culling of distant objects and stuff like that. Is that something that is, that can be, let's say, that the system can actually tweak locally depending on the user hardware, or is it something that is just restricted by the way the generator and all that stuff works?
So it's certainly something we could tweak based on hardware, but in terms of looking at that, I'm glad you asked, because we got objects drawing a whole lot further. Personally I did, so it's a good thing. We've got trees really far away. But also, I think a lot of people look at our demos and think that our draw distance is really close in, when actually we have just done a lot of work on bringing fog closer in and further out at different points. So if you're seeing objects fading in front of you, then yes, that's something that we are, what we already have done work on, and is definitely pretty good. And if you're talking about the world at distance and how far you can see in total, then that's more down to atmospherics than.
All right, gonna take another question from the stream.
Okay.
Regarding the generation of trees, is some sort of L system in use? If not, how exactly are branches built? How do you restrict intersections?
So I guess this is for generating objects and things. We don't precisely use L systems, but we do essentially use something that is a whole lot like L systems, enough that we may as well call it an L system, for putting together bits of geometry. So We'll be starting with that base rig and base shape that the artists are making, and then it will be an L-system-like way of combining branches on top of that. Because it's easy to think of a tree in terms of an L-tree structure, but it's not that hard to think of other objects like creatures and things in terms of putting them together that way.
Hello. How do you deal with levels of detail on terrain and the triangle density? Because I assume you're using dual contouring on uniform grids.
Yeah, so the way we deal with LODs is we keep all of them around after they've been polygonized. So by having a lower density of voxels, then when we run the same dual contouring code, we immediately end up with the same density of triangles as we originally had voxel data. So that means that our second LOD of voxel data is immediately twice the scale of our nearest one, plus some modifications for our non-uniform voxel density.
All right, another question from the stream. How do you generate landscape that have intrinsic structure, valleys, rivers, with BCG systems that are purely local and can't rely on neighboring tests?
So a lot of the way that we do it is just having different shapes and filters that we can apply on a local basis, but that are noise-based to make something that might be height map, applying over the top of it and making it look like it's been eroded so that we can modify slopes in that way, if you see what I mean. So we start with a basic mountain, you apply a filter on top, and even though it's only looking at every individual voxel, it then starts to take on the shape of being eroded for that amount of time.
Okay.
Hi. So you said that you use the positions for the seeds, so how do you handle planet movement?
How do I handle what, sorry?
The movement of the planets.
Oh, the movements of the planets, well, they have an initial, like they have a location within the solar system. I mean, they have a start position. The way that we think about things like that, well, personally, I like to think of it in a kind of functional reactive programming kind of context, so that things will have a start position and they have a position at a certain time, but they have a constant seed. And when you arrive at the solar system, then you're able to evaluate where everything should be. And that goes for like creatures on a planet, ships flying around, that kind of thing.
Thanks. And then another short question. How do you handle the coordinate system? Do you have a 64-bit floats or fixed point or what?
For the seeds or for the vert data? For the positions, we tend to handle it. We don't use 64-bit positions. We just tend to handle them in groups of different precision. So.
All right, thank you very much. We will have more time for questions in the panel later today. Let's thank our speaker one more time.